What is up, athletes? So let's go ahead and let's work on confidence intervals when they provide you with the population standard deviation. And remember, we use the sigma, the notation sigma to describe that. So let's look at some problems here. All right. So for those of you that are in my class, we're looking at section 8.1. But regardless, we're looking at confidence intervals, constructing confidence intervals when they provide you with sigma, which is our population standard deviation here. So let's look at this. All right. So in the simple random sample of 165 households, so right away, what I like to do is start labeling things. So that is our n value, right? So they provide us with n. The sample mean, which is our X bar, is 1.82. So make sure you're labeling all this. So this is X bar. Assume that the population standard deviation is 0.96. All right, so the program I'm about to show you. So again, today we're focusing on using our calculator work and understanding what happens to our confidence interval as we alter some things. All right, so here they're asking us to construct a 98% confidence interval for the mean number of personal computers. So what this is going to do is it's going to provide us with a window. And what we're saying here is we're 98% confident, right? If we did this 100 times, right, this method is going to work 98 of those times. That's what we're saying here, right? 98 of those times, it's going to provide us with a window where the true mean of the population is going to fall inside. Okay, so let's go and let's use our calculator. So let me get new. So this is, we're going to use stat test, and then you're going to go down to Z interval. So the difference between Z interval and T interval, because we will use T interval in our next section, is notice they gave us sigma. When we use T interval, what we're going to have is our sample standard deviation. All right, so make sure you make a note of that. Here they give us sigma, here they're going to give us S. That's going to be the big difference. So we use Z interval. Data is when they give you a list of values. All right, so we're going to use stat, and we just enter our information. So let me go back real fast and grab that. 1.82, so our standard deviation, they tell us is 0.96. Let me erase the 0. Doesn't matter though. X bar we said is 1.82. So X bar 1.82. And I think we said 190, 165. And then we're 98% confident. So again, this calculation here, calculate, enter, is going to give us our confidence interval. All right. So the true mean of the population. So if we had every single computer, the mean would fall between 1.65 and 1.99. Right. So that's what we were saying. So let's go back. And so our first one, just a reminder to check your assumptions. So number one, make sure this information comes from a simple random sample. And number two, make sure your n is large enough so that the population is approximately normal. So here our n was 165, so we're okay there. Okay, so that's what allows us to use to go through this process. All right, so we use Z interval, and we got these values right here. All right, so this was our confidence interval, or 98% confidence interval. And if you wanted to use Excel, they run through how to do that using Excel. But again, we're sticking with our TI 84 calculator, or if you're using the app. So we're 98% confident that the population mean for the number of computers will be between 1.65 and 1.99. All right, this is where a lot of you guys are having trouble, and I want to kind of interpret what the heck they're saying here. So I don't want to use their answer. I want to make sure you understand what's going on. So let's look at the question. Part B. If our sample size were 120 rather than 165, so notice our sample size got smaller, would the margin of error be larger or smaller? So this is where I encourage you guys to start creating some type of table to help with your understanding. So what I'm going to do here is let me write down our formula. So in class, I highlighted the importance of knowing the formulas to help with these deeper understandings. So let's say, so our formula to construct a confidence interval was X bar plus or minus a Z times sigma divided by the square root of n. And this piece right here, that I'm going to put in parentheses, this is known as our standard error. So whenever you hear them talk about standard error, that's this piece. When they talk about margin of error, that's this piece right here, Z times this quantity, Z, sigma divided by square root of n. All right, so this piece right here, what you're adding and subtracting, all of it, this is called our margin of error. All right, so let's make some notes here. So if the sample size were smaller, so when n is smaller, so if n gets smaller, well, look what happens. You begin to divide by a smaller number, right? So when you divide by a smaller number, what happens is your answer is actually bigger. Okay, because you're not dividing by some large number. Because if remember, when you divide, the bigger n gets, the smaller this whole thing gets. So when n gets smaller, the margin of error gets larger. So the margin of error, I'll just call it the margin of error gets larger. So when n gets smaller, the margin of error is going to get larger. And then vice versa. If n gets bigger, then the margin of error gets smaller. And what that means is the greater your sample size, right? If you want less error in your data, what you do is you start collecting more data. And the bigger your data set, the more accurate it's going to give you. So you're not going to be way off, right? Whereas if you only have a few values, you could really be way off. And so again, if n is smaller, you're going to have a larger range. Right? That's one thing that impacts our confidence interval there. All right, so that's going to help you with part B. Part C, now it's talking about, well, what happens if the confidence levels were 90% rather than 98? All right, so let's write another little note. So again, using the same formula, if the confidence interval, sorry, if our confidence level, we'll call it CL, our confidence level decreases, gets smaller. So if our confidence level decreases, if it gets smaller, what would the margin of error, what would happen there? So in this case, our margin of error, we'll just call it margin. All right, so let's check this out. So the confidence level, what it does, it's like a light switch. It controls how dim Z value is. So the smaller your confidence level, the lower your Z score gets, your Z value here, right? So if this is smaller, you're going to start to multiply by a smaller number. And this becomes smaller, right? So your margin of error becomes smaller. So when your confidence level is smaller, your margin of error is smaller. So remember what we're doing is we're getting two numbers, we're getting a range. And when you're less confident, that means that range is going to be smaller. right? But when you're more confident, hey, my answer is going to be between here somewhere. Well, why is that? Why are you more confident? Because what happens is your range starts to get wider, right? Your basket starts to get bigger. So your confidence increases. So again, when your confidence level is smaller, the margin of error is smaller. But when you increase that confidence level, right? When you increase that confidence level, the margin of error gets larger. All right, so make sure you got that down. Based on part A, is it likely that the mean number of computers is greater than 2.13? And I noticed a lot of you guys were getting this wrong. And so I don't think this definition was really helping. Let me clear this. Because again, I look at the buttons you guys press, and then people are saying, no, it's not likely that the mean number of computers is this, but let's see where their explanation was. Since none of the values in the confidence interval is greater than this, it is not likely that the personal computers is greater than that. So people are like, wait, what does that even mean? So again, what you're doing is remember this answer that we got right here. So 1.65 to 1.99, right? So what we're doing is that interval, our mean is going to be somewhere in here. The population mean is going to be somewhere between those two numbers, right? But they're trying to say, hey, is it likely that our answer is going to be greater than 2.13? Well, 2.13 isn't even inside of this range, right? 2.13, what they're asking us for, is outside of this range, right? So we're saying, hey, the mean is likely, really likely, right? This thing's going to work 98 times out of 100. Our population mean is going to be in here. And now they're asking us, hey, do you think it's likely that it's going to be above that? So we're going to say no, right? Because this is nowhere inside of our range. All right, so I hope that helps out. Let's do another problem here. Let's do question 4. All right, and this one, notice this one is different than our last one because now they give us a list of values. So what we're going to need to do is we're going to need to enter all these into list 1. So just a reminder, just like we've done in the past, you're going to go and your first step is going stat, edit, and then you can put in whatever list you want and go ahead and plug those numbers in here. If you have values in here like I do, remember you could go to the top, highlight that, make sure it's highlighted, and just hit clear. And then go in and start plugging in your numbers. Okay, so just a reminder of how to do that. So after your numbers are plugged in, right? So let's go through the process here. So that's going to be your first step. All right. What we want to check for is this distribution here, right? Is it approximately normal? So if you guys remember from 2 homeworks ago, they would give you a dot plot just like here, and we would see, is it approximately normal? So if we created a dot plot, we would look at this and we would make that judgment call, is this approximately normal, right? So there's 2 things we need to check for because look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a small sample size, right? So that sample size is less than 30. All right. So what we got to do is we got to make sure if we're going to use this information, is our distribution normal? So what are you looking for? All right. So when we look at this dot plot, we want to see, hey, does the sample contain an outlier? Does the sample exhibit a large degree of skewness? Right. And is the sample multimodal? Does it have more than one distinct mode? All right. So here, when we look at it now, number one, it is because it's going to ask you, do we need to check if it's normal? Well, yeah, because look at this. Our sample size is less than 30, like we said, right? We have a small sample size. And by our graph here, our distribution, we could see that we have an outlier over here. So most of this information is pretty close to each other, but then we have this guy all by itself. So this would be an outlier because most of our scores are somewhere inside this range, but this one's way the heck out of here. The sample contains an outlier. So I wouldn't even go through this process in terms of trying to construct a confidence interval for this data because number one, this data isn't approximately normal and our sample size is too small. All right. So again, they're just kind of getting you used to make sure you check your assumptions before you begin. All right. So let's look at this one. So this one, again, we could run this through our calculators. We could look at our dot plot that's going to be presented to us. And we have a small sample size once again. So we need to make sure we check our assumptions. So in this case, right, look at our dot plot. So does it contain an outlier? The sample exhibits a large degree of skewedness. The sample is multimodal, right? It has more than one distinct mode. So these are the things we're always checking for. So if one of these fails, right? If we see one of these happen, then we're going to say, you know what? This is not approximately normal. All right. So we look here, and based on these values, again, what you're going to do is enter these values into your calculator and remember the section where we created Q1, Q3, and then we did an IQR, and we did our lower boundary was Q1 minus 1.5 times the IQR. And that formula plus the Q3 plus 1.5 times IQR, that helped us determine if there's an outlier. All right. So if you need help with that, I'll link that video to determine how do we determine if there's an outlier. So you follow that formula. And when you do, you're going to see that this graph right here does not contain an outlier. All right. Based on how our distribution, how our values are spread out. So again, go back and look at our, it was our 5-number summary and then determining if we had an outlier. All right, so I'll link a video to that so you could get some more practice. We don't have a large degree of skewness here, and there's no evidence that the population has more than one mode because the only number here, there's only one mode. All right, so what that does is that allows us to go ahead and proceed and construct a confidence interval. All right, so we're going to use our TI-84 to construct this 99% confidence interval. So like we said, we enter everything into list 1 or whatever list you want. And the only difference is when you go to test and Z interval, just make sure you highlight that data option. So if I take you to the calculator real fast, let's pretend I had stuff in here. All right, let me hit quit. I'm going to go to stat, test, Z interval. But this time, instead of hitting stat, I'm going to hit data. I enter in the standard deviation, this population standard deviation that they give me, and then I'll hit L1, and then 1, and then put the confidence interval. All right. So again, it's very similar to what we did before, but now they're giving us data. All right, so let me go back to my other screen. So that's what they're doing here, right? They're walking you through that process. So you plug in everything and boom, they provide you with your confidence interval. So this is our confidence interval for, what was it, 98%, I believe. All right. Well, 99%. All right. So we say we are 99% confident that the mean calorie count for all 12-ounce milkshake sold at this fast food restaurant is somewhere right inside here. So this interval is going to contain the true population mean. So notice it's not giving us the exact population mean, because in order for us to get that, we need to have all the data. And a lot of times that's impossible or really, really hard to obtain. So what we're doing is we're getting an idea. Oops, it's my alarm clock. Is we're getting an idea of, hey, where does that population mean live? More or less, where is it located? And we say we know, we're very confident that it's located somewhere inside this range. All right. Excellent. So those are the two problems that you guys are going to encounter in this homework. So if you have questions, make sure you let me know, and have yourself a wonderful day, Mathens.